my name is Chi. I will carry out the BSC121 presentation for differentiation and integration. You can look at the contents, including three parts. The part 1 is application of derivatives to economics, and the part 2 is the working method. Part 3 is moments and center of mass. Part 1 Application of Derivative to Economics 1. Marginal analysis. Derivatives are used to calculate marginal revenue and marginal cost to help consumers and the business make more informed decisions. 2. Elasticity analysis. Derivative can help to solve problems that maximize and minimize an objective function. 3. Optimal problem solving. Derivatives are used to analyze the sensitivity of economic variables to changes in income, interest rates. Functions 1. The cost function is written in the form of Cx. The derivative of the cost function represents the marginal cost, i.e., the cost per unit increase in production. If the derivative of Cx is low, it indicates high productivity. If the derivative of Cx is higher, it reflects a rapid increase in cost. 2. The average cost function is written in the form of Acx. The derivative Acx indicates the rate of change of average cost with output and can be used to analyze whether there are economies of scale. If the derivative of Acx less than 0, average cost decreases. If the derivative of Acx larger than 0, average cost increases. 3. The revenue function is written in the form of Rx. The derivative Rx represents the marginal revenues, i.e., the additional revenues generated by an increase in one unit of production. 4. The average revenue function is written in the form of ARX. The derivative ARX reflects the trend in average income and is usually related to price elasticities. 2. 5. The profit function is written in the form of Px. The derivative Px represents the marginal profit, i.e., the effect on profit of increasing production by one unit. Profit is maximized when Px equal to 0. Profit is maximized when the derivative of Px equals to 0. 6. The average profit function is written in the form of APX. The derivative APX represents the change of average profit with yield. 3 practical examples. Example 1. Marginal cost and optimal yield. The cost function for a factory is Laplace function, and the marginal cost is the derivative of this function. Assuming that the market allows a marginal cost of 250, solving for this function gives x equal to 10. Thus, the factory reached the marginal cost limit at output 10. Example 2. Profit maximization. The revenue function of a firm is this function, and the cost function is Cx. The profit function is Px equals to Rx minus Cx, and the marginal profit is the derivative of Px equal to 150 minus 2x. The profit maximization condition is the derivative Px equal to 0. So 150 minus 2x equal to 0. To get the x equal to 75, the optimal output is 75 units. Example 3. Minimum average cost. The cost function of a firm is Cx equal to 100 multiply x plus 5,000, and the average cost is Acx equal to this function. We can calculate the derivative of the Acx. The derivative of Acx less than 0. Average cost decreases with production, but tends to 100. Fixed cost sharing is weaker. Part 2. The washer method. Sometimes slicing a solid of revolution results in the discs with holes in the middle. We call them washers. We can assume that the Fx is the outer radius of the washer, and the Gx is the inner radius of the washer, and the A to B is the interval along the x-axis. If the region is rotated around the y-axis, the formula is adjusted to integrated with respect to y, using the corresponding radial function fy and gy. Part 2 example. Find the volume of a solid generated by revolving the region bounded by y equal to x squared and y equal to 4 around the x-axis. Step 1. Draw and analyze the area. Y equal to x squared is a parabola with an upward opening and a vertex of 0.0. Y equal 4 is a horizontal line. The intersection of the two curves is the intersection of the y equal to x squared and y equal to 4. And then we can get the x equal to 2 and x equal to minus 2. Step 2. Rotation volume formula. We can assuming that fx equal to 4 and the gx equal to y and then equal to x squared. Therefore, the volume formula becomes this function. Step 3. Simplify the expressions. According to the symmetry about two-axis symmetry, the upper bound of the integral is changed to 0 to 2, and the result is multiplied by 2. Like these functions. Step 4. Calculate 1. Split into two parts and calculate part 1, then calculate part 2. 4. Combine the result. Part 3. Moment and the center of mass. The point on which a thin plate of any given shaped balance is called the center of mass of the plate. If the region R lies between the curves y equal to fx and y equal to gx, where fx is equal and greater than gx, the center of R is bar x point bar y, where is these two functions, and the product of the mass m of a particle and its directive distance from the point is called the moment of the particle with respect to that point. The moment of the region R about the y-axis is this point, and the moment of the region R about x-axis is this function. Part 3 example. Find the center of mass of the region bounded by y equal to x squared and y equal to 4, assuming the uniform densities. Step 1. Analyze the region. The region is bounded by the parabola y equal to x squared and the line y equal to 4. The horizontal limits are x belong to -2 to 2, determined by solving x squared equals to 4. Step 2. Total mass m. Since the density is uniform, the total mass is equal to the area of the region, like this function, and calculate it. 1. Compute the first term, like this function. 2. Compute the second term, like this function, and we can calculate the total mass is 32E3. Step 3. Moments mx and my. 1. Moment about the x-axis. 2. Moment about the y-axis. And then we can calculate the mx is 256 in 15, and the my equal to 0. Step 4. Coordinate of the center of mass. The center of mass coordinates are bar x equal to 0 and bar y equal to a in 5. That's all for my presentation. Thank you.